Hello and welcome to this presentation about understanding the hardware and software which implements the interrupt mechanism within the MC1322x. This is part 2 of a presentation about the hardware that was started earlier in this semester. So let me start off with talking about the timer. The way we have decided to go on with this presentation is to kind of define some of the most important functional units within this chip. Starting off with the timer. The timer module is purposed to count internal or external events and compare the values within the preset values. So it's note that the timer is really important because it's one of the peripheral devices that can generate interrupt requests. Now, the external inputs of each counter or timer are shareable and can be used as count and timer commands, trigger to capture the current value, and interrupt requests generator. Now, the timer is also a programmable part of this unit, so you can basically program it. Next, we talk about the timer module, which recognizes a few types of interrupts. First, the timer compare interrupts, which is generated when a match occurs. Second, the timer overflow interrupt, which is generated when a counter rolls over its maximum value. And third, the timer input edge interrupts, which is generated when there is a transition of the input signals. The timer module has several functions or modes, with each mode counting different types of external signals. So there is the program counter as well, which is an important unit of this chip, where register 15 holds the program counter, or what we call the PC. Next, I'm going to define and talk a little bit about what exception vectors are. These are basically addresses of the service routine, which is generally hardwired. So the ARM7TDMIS processor, that's what is the actual processor we're talking about, when it accepts that its exception vectors reside at memory addresses starting at 000 to 001F. However, the ROM is mapped into the low memory address space, which is 000 through 3FFF, and as a result, the exception vectors also reside in ROM and are hard-coded. So, the ARM architecture places the exception vector addresses generally at the bottom of the memory map, that is, at the starting address of 000. With the MC1322x, the onboard ROM is located at address page 000 and does not allow the user to change vector content. Obviously, anything that is ROM cannot be changed by the user. To overcome this issue, the ROM redirects the vector table to the base of the RAM at address 0040000. And in that case, we have what we call the jump vector table, and here it is. This is from the documentation of the MC1322x, and as you can see, we're mostly interested in the particular IRQ, which we will talk about in a bit, but this is the mapping between the ROM address, which is 0018, and the RAM address, which is 400018. So this map helps us unload the information from the RAM and put it into the ROM for the device to start processing the exception IRQ. Now, I'm going to jump a little bit and start looking at the code that we were provided with, particularly at certain modules and functions, and we will try to point out the areas of interest in relation to the interrupt mechanism of this chip. So to start off, I'm talking about the file that is start.s, which is, in our opinion, it's something like an assembly language type of construct over there within the file, and it's located in the source. As you can see, there is a bunch of lines here which actually map to the different modes that we just talked about, and in particular the IRQ, which is the interrupt request. So let me talk a little bit about the interrupt request, which is a mode that is used for general purpose interrupt handling. The interrupt request, also known as IRQ exception, is a normal interrupt caused by a request on the IRQ internal signal. IRQ has a lower probability than something called FIQ, which we will talk about in a minute. It is masked on entry to an FIQ sequence. So an IRQ can be disabled at any time by setting the I bit in the CPSR from a privileged mode, and we will talk about that bit in particular in just a few slides from here. Now, the interrupt modes are entered as exception processes. So, exceptions arise whenever the normal flow of a program has to be halted temporarily, for example, to service an interrupt from an external peripheral. And so you can disable IRQ at any time by setting the I bit, as we talked about, from a privileged mode. Now, an IRQ handler returns from the interrupt by executing what is known as a sub-S program counter, and then R14 IRQ. And we will talk about this. So basically what happens is the interrupt request must be shut down so that the system does not make a second request for the same interrupt and reinitialize the same request and instruct the program counter to duplicate the interrupt service request procedure again in error. This would also include popping the program counter address of the state just prior to the interrupt being received off the stack and returning to the previous program execution, likely more interrupts. So here's how the general process looks like. First, we pop the interrupt program counter location from stack, then we disable the IRQ and return to the IRQ mode, then we pop the current program counter from stack, we pop the pre-IRQ registers from the stack and restore registers. We retrieve the executed IRQ vector location. We acknowledge the IRQ has been serviced and return from the ISR. And finally, the ISR is considered complete and we close out. Now, another important functional unit that we need to consider is called the ITC, or the interrupt controller. So what is it? Let's talk about it in a bit. So the ITC is a peripheral function that resides on the CPU data bus, which collects interrupt requests from the peripheral sources and provides an interface to the CPU core. Now, the MC1322x MCU interrupt structure is based fundamentally on the ARM processor. The interrupt control is distributed across the peripheral devices. The interrupt controller, which is what we're talking about, and is known as ITC, and the CPU control. And we will talk about the CPU control in few slides from here. The ITC driver simplifies programming of the ITC module. Now let's have a look at the diagram that we have here. I'm going to zoom in a little bit and first talk about request management. So the interrupt controller accepts the interrupt request from each module source. It could be an SPI, a UART, or a timer. Any type of request will basically, with multiple requests, that gets prioritized and mapped to one of the two basic requests to the CPU. That is, we have two options, the fast interrupt request, which is known as the FIQ, and the normal interrupt request known as the IRQ, which we talked about in the slide. The interrupt requests are generated within a peripheral function. Each function has its internal interrupt request sources channeled to its single IRQ signal. The ITC then prioritizes these requests and maps them to either the IRQ or the FIQ inputs to the CPU. Now, I want to look at something in particular here after dealing with this ITC. In particular, we found out that the ITC base address is actually 8002.0000, and looking at the code within the library folder and the include folder, there is a file called isr.h, and if you look at line 41, we notice that we have basically the same address right here in the program code. Next, I'm going to talk about a very important register, which is called the int num, or interrupt enable number register. Now, the interrupt enable number register provides a hardware accelerated means of enabling of interrupt requests. This hardware mechanism alleviates the need for an atomic read or modify or even write sequence to enable an interrupt source. Writing to certain fields enables the interrupt source associated with this value. Now, here is a table, which is the table for the ITC register memory map, and if you look at it, you notice that there is this highlighted row which talks about the interrupt enable number register and it being a 32-bit only write register. And you can also look at the offset, which is 08. And now if we look at the code, particularly at the folder lib/include and the file isr.h, we can see that all of these particular interrupts, not just the int num, but also the other ones located in this table, can actually be mapped right into the code right here as an enum starting at number 0. And if we look a little bit also down here, we notice that we have the function enable IRQ, which is passed a variable that is called IRQ. In our case, for the case of our LED light, we are basically passing the timer in this case. And notice also at the end of this line, the way the int num and there is double hash IRQ, this is also some kind of representation that basically means concatenation. So let's look at the same file, looking at isr.h. Now we can see also that there is a definition of all these offset addresses, and they are being added to the base, as you can see right here. And this in particular is what we are looking at, the int num. You can see that it's composed of a base address and also an offset. And moving on, I want to talk about the ISR, or what is known as the interrupt service routine. Now, in order to service the different interrupts generated by the timer, the interrupt controller must be configured to enable the interrupts for the particular timer being used. Additionally, the user will need to write an interrupt service routine. Again, as explained in class and as found throughout the code of this library, we notice that there is an interrupt service routine. That's where the programmer or the developer would actually put the code, which will be run as soon as the program counter changes and as soon as the interrupt gets serviced. So let me move on to say that additionally the user will need to write an interrupt service routine, of course. So looking at our code and looking at the source folder with the file isr.c, we can have a look at a number of interesting things here. In particular, you can see that we do have the int num. For example, we have the I2C, which is something that we will look at in a future presentation. But for now, let me talk about the CPU request service. In particularly, the ARM processor has 7 operating modes, and 2 of these are used to service interrupts. As we mentioned, we have a fast interrupt called FIQ and a regular interrupt, or a basic one, called the IRQ. The first one is a mode which supports a data transfer or channel process, whereas the second one is a mode which is used for general purpose interrupt handling, such as interrupts that are coming from a timer. Now, the ARM core has Program Status Register, which is known as the PSR for exception handling, which we will talk about as well in a bit. But for now, we need to know that the interrupt modes are entered as exception processes. So exceptions arise whenever the normal flow of a program has to be halted temporarily, for example, to service an interrupt from a peripheral. There are 7 exception conditions, and when multiple exceptions arise at the same time, a fixed priority system determines the order in which they are handled. The ARM core imposes the following priority among the various exceptions. So we have reset priority, we have a data abort, we have fast interrupt, normal interrupt, prefetch abort, undefined instruction, and the SWI. And looking at the start.s, we can see how all of these modes, so to speak, are being hardwired or are being loaded into the program counter. So basically, this is an initial step in initializing the device, where each of these modes are actually being set into the device. So the PSR, which we just mentioned a while ago, is important because it will handle the return of the program control after the routine is executed. And that's important to note because when the CPU runs that particular service routine, it needs at one point to go back and resume whatever program execution was taking place. And that is the job of the PSR. So the PSR includes current program status register, known as the CPSR, and 5 stored program status registers, known as the SPSR. The program status register, what it does, it holds the condition code flags, it controls the enabling and disabling of interrupts, and set the processor operating mode. And this figure we got from our document as well. We mentioned a while back talking about the I bit, and there you can see it's connected, it's bit number 7, and it is related directly to the IRQ, so you can enable and disable that particular bit. And now moving on to talk about, again, the program status register. Before attempting to handle an exception, the ARM core preserves the current processor state so that the original program can resume when the handler routine has finished. So, it preserves the address of the next instruction in the appropriate LR, which is known as the load register. Second, it copies the CPSR into the appropriate SPSR. It forces the CPSR mode bits to a value which depends on the exception. And finally, it forces the PC to fetch the next instruction from the relevant exception vector. Having looked at all the different definitions and particularly the code that is related to those functional units, I would like to just have a brief look at the program flow that we had looked at earlier. Starting with the start.s. Again, this is the area that we mentioned before. This is an initialization script, if you want to call it. It basically loads a lot of predefined addresses and data into particular registers, basically setting the different modes of this device. In particular, we had 7 modes right here, including the IRQ, which was of interest to this particular presentation. And I want to also look at the timer int s.c, which is our main program basically. And within it, there was this particular function, which is called the tmr0 underscore ISR. And we were kind of intrigued by the fact that this function was not really called in the main. And looking at, obviously, if you want to say hacking the code or looking deep into the folder structure, we were able to locate how this function is pretty much hardwired into one of the interrupt service routines. So this is exactly what we are talking about. This is the service routine which gets called or gets hardwired whenever whenever an interrupt needs to be serviced. So what we're doing right here is simply toggling the LED on and off, and we are also clearing the timer 0 control flag so that it restarts all over again by counting down or counting up. And when the timer hits 0, the hardware signals an interrupt, and it gets processed by the CPU one more time. Looking at this timer in ts.c file, looking down at the code at the bottom of this file, we notice that our main functionality lies in turning the LED on in the beginning, enabling the IRQ, or enabling the requests from the timer. As you can see, the timer is a variable here, and then running into an infinite loop, waiting for that interrupt to happen, or waiting basically for the timer to signal an interrupt, which gets later serviced by the CPU in the form of executing a particular function, which we call a routine handler. So looking at the file within the lib folder and include, it's a file called isr.h, we notice something. We notice that there are 2 functions that are defined here, enable IRQ, and as you can see, it's using a pointer or a pointer reference to a concatenation between a base variable called int_num and concatenating it with the variable IRQ. So basically, if the IRQ was a timer, then in this case, the variable would actually be int_num_tmr, or it could be anything else. So this double hash sign means concatenation. That's what we're talking about. Now moving on to another particular module which is found in the lib folder. It's called tmr.c. It's also interesting because, as you can see, it has the enable IRQ, and this is where we're actually passing the TMR, our variable, the timer. And finally, there is this file which is isr.c found in the source folder. And this was interesting too because this is another way of writing functions and kind of linking the IRQ function to the underscore IRQ that was presented earlier in the slides. So as you can see here, this function, the way it handles the requests is it first checks if the bit is set. In particular, it checks if we are actually dealing with the interrupt that is coming from a timer. And because it doesn't really care which timer it is, we have to manually do an if-else check on the different timers, being it timer 0, 1, 2, or 3. And as you can see. And that pretty much concludes our presentation about the hardware-software interrupt mechanisms, and hope you enjoyed this presentation. Until next time, have a good day.